Good afternoon, everybody. We'll be getting started in just a couple of minutes. Thank you for joining us today. Okay, I think we're going to go ahead and get started. My name is Sean Maurer. I'm a mechanical engineer with the Smart Energy Design Assistance Center. Joining me today is my colleague Ryan Siegel. Today we're going to be overviewing commercial site inspections, some key items to be aware of for that commercial site inspection visits. Today's webinar is being recorded and will be available on our website along with a PDF of our presentation after this event concludes. Controls are on your screen. If you would like to ask a question, please use the question and answer window. You should be able to hover over the bottom or top of your screen, and it should be in the center of the selection bar there. If you do enter a question into the Q&A, that will allow us to answer your question live, keep track of it better. If we cannot answer your question live, it provides us with your contact information so that we can follow up with you after the webinar. If you do enter a question in the chat window, it is a little harder for us to follow up with you. So please do make use of that Q&A window. CDAC is a preferred education provider with the International Code Council. Credits can be earned on completion of this program. I will report that to the IECC for you for continuing education credits. We also issue certificates of completion after the conclusion of the webinar for all participants. They will be a little delayed this week. They'll be coming out early next week. Also, for AIA members looking for continuing education credits, if you reply to the email with your certificate of completion with your AIA member number, we will submit those credits for you as well. Today, we're going to be covering commercial site inspections. We want to understand the Energy Code site inspection practices for commercial buildings. We're going to learn which measures generally are not meeting the Energy Code requirements during that construction phases, and demonstrate how to comply with the Energy Code requirements at the site inspection stage. The Smart Energy Design Assistance Center is an applied research program at the University of Illinois. Our mission is to reduce the energy footprint of Illinois and beyond, and these presentations on the Energy Code are one facet of our many operations to do so. This training is brought to you by the Illinois EPA's State Energy Office. We'd like to thank them for sponsoring these trainings. CDAC provides technical support for those with Energy Code questions. Technical support can be reached at energycode@illinois.edu or at our 1-800 number listed on the screen. We also have a wide array of resources available online at smartenergy.illinois.edu/energy-code. At that site, you will find access to our previous workshops and webinars. We also have some self-paced online courses. These are training modules that are designed for people who aren't familiar with the codes, so a little bit lighter than the technical content we get into here, and also has direct links to our technical support email address and phone number, so you can find that information easily. We also have links to Energy Code resources, such as links to the IECC, most current versions, also the Illinois amendments and the Chicago Energy Code amendments as well. So they're all in an easy to locate location. This webinar is part of a series of workshops and webinars on improving compliance with the energy code in the state of Illinois. Our past webinars have included commercial site inspection today. We'll have an energy code panel discussion coming up on June 15th, and commercial HVAC will be covered on May 26th. So as we're moving into our presentation, first thing we need to know is when does the energy code apply, when you're going to need to be concerned about site visits for your facilities and compliance with the energy code. The International Building Code, Chapter 1, Section 105 contains exemptions from building permits. If you are exempt from a building permit for your project, you will not have to comply with the energy codes for that particular project. The list on this page is in general things that are exempt from the permit, but check with your local building office as these do vary from municipality to municipality. It's always good to check on the specific requirements for the place where your work is. The next thing you need to know is, are you in a commercial building? The energy code defines a residential building as a detached one-family or two-family dwelling, or any building that is 3 stories or less above grade, 4 stories or less in Chicago, that contains multiple dwelling units in which occupants reside on a primarily permanent basis. So that would be townhouses, row homes, apartment houses, a convent monastery. The key phrase being that primarily permanent basis for residences. If you do not fall into that definition of a residential building, then you are a commercial building. So all other sites would fall under the commercial provisions of the energy code. And now I will turn it over to my colleague Ryan Siegel. He'll go over the envelope requirements for site inspections.
Thank you, Sean. So now that we've hopefully determined we are looking at a commercial building, looking at footings and foundations to start, and understanding that each of these may depend on the local municipality and how they handle inspections as far as when the different inspections might occur, or some of these may be covered as part of other inspections during the construction process. So the code actually specifies the various inspections that are required. So here's a listing of information for footings and foundations that it requires for inspections. And so one of the first things that we're going to be checking for is what's the insulation depth. This is a screen capture out of the ComCheck software, which actually is very good at depicting what, how do we actually measure the insulation depth, such that we understand where we are, how much of this has to be below grade, what is the total height. We also will, as part of this, is understanding that insulation depth is typically assumed to be full height. In ComCheck, it does allow you to specify what the various things are, and understanding that the rim board, the rim joist area, is included in above grade wall area. It's not part of your foundation wall assembly. So being aware of how you're measuring that. So as you see in the illustration here, it starts from the header and goes all the way down from there. So the floor is part of the wall assembly above. So first thing that we're going to be checking as part of an inspection is, is the insulation located where it was supposed to be? Are we using interior insulation versus exterior insulation? This can have an impact, particularly for concrete walls, and understanding, are you being able to take advantage of that thermal mass of that wall? If the plan called for insulation on the exterior of the wall to take advantage of that thermal mass, but it's located on the interior of the wall during construction, that can be a problem for your design. And also looking at, are we specifying cavity insulation versus continuous insulation? Cavity insulation is bridged through structural members. continuous insulation is not. And that continuous insulation would only provides for thermal bridging due to fasteners and service openings. So if you have like a continuous Z channel across it, that would not be continuous insulation, because that's not just at the fastener locations. So being aware of that. Then as we're going through, and again, as I noted here, Z channels would not be would be bridging through that, so that would be not providing that continuous insulation. And where the furring can be on the inside of the insulation, and by using furring strips, this can provide some additional room for rough ends of electrical, or even nowadays more and more data we're seeing run there in these walls. So furring strips on top of continuous insulation is definitely preferred. You don't, again, trying to avoid introducing a thermal bridge for that continuous insulation. Something else that this continuous insulation can help avoid is, particularly if you have metal wall studs, those are extremely conductive and commonly eliminates or substantially diminishes the effectiveness of your insulation that you paid for. So being aware is part of that. Next, checking to see, do we have the appropriate R values? Do we have the required quantity, and does it match the design? More insulation is generally perfectly fine. You just need to make sure that it's not less. Something to be aware of is a lot of insulations, being aware as far as how they're installed dramatically impacts their performance. Here on the left, we're showing a bat product that's labeled an R19, but we notice here in the picture it says that it's a 6¼ inch thick bat. Most 2x6 walls are going to be 5½ inches thick. And so looking a little closer, when you compress that 6¼ inch bat into the 5½ inch cavity, that reduces that effective R value. It goes down from an R19 to an R18. May not be substantial for your project, or it could be rather dramatic. If it called for an R19 and you put this in a regular 2x6 wall cavity, then you're not meeting what was called for in the design. So what you'd probably end up having to do in that case, if you needed the full R19, is for a new wall, you're going to have to fur that 5½ inch stud out an extra 3/4 inch. So in order to fit it all. Once we have our R value, again, checking that thickness, and we want to avoid any compression of that insulation, and make sure that we fill that whole cavity. Without that, what we can end up with is convective currents, and air can move within this thermal assembly here. Depicted on the left, we have some metal studs, which as noted earlier, is going to provide substantial thermal bridging. And so if this is supposed to be for thermal insulation, you can see there's a lot of potentially compression, or this product is not filling this cavity. Now, if this was an interior wall and this is for sound dampening, there you probably don't want that cavity to be fully filled for sound isolation, such that you don't end up with a easily conductive path through the cavity. So again, checking, have we compressed that insulation, and have we filled the cavity? Because without filling that cavity, again, those convective currents can occur in the wall, diminishing the effectiveness of your insulation. Also, during the footing and foundation, we're going to be checking for the depth of burial. Is it going down as far as it was specified, whether that's 2 foot or 4 foot? Some places we see specified going down as far as 10 foot below grade. Now, some of this, the code does allow to be horizontal. So it could be such that if you need 4 foot of insulation, you may see a installation where it goes down 2 foot and then comes out from the wall by 2 feet. So that would be perfectly fine for most designs out there. And again, what we're trying to do is isolate the cold exterior. And so by having that insulation be on a horizontal, that path of cold is going to have to come down 2 foot and then back 2 foot in order to reach that foundation. So that's part of the reason why they do allow for horizontal insulation for part of this, because again, we're allowing that longer path for heat transfer. Once we have our insulation installed, we need to make sure that we have protected the insulation from various hazards that can be damaging to insulation. Probably one of the most common out there is going to be UV damage or physical damage for insulation above ground. And one way to provide that protection for horizontal insulation is that it does require the code does require that it has to be buried at least 10 inches below ground or protected by pavement. So again, by being at least 10 inches below ground, you're less likely to have a landscaping shovel or something similar pierce that insulation and eliminate the effective path for that. So here we're showing on the left-hand side, this is a insulation product that's looks like being overlaid by a stucco coating. And so that's providing some of that protection against physical damage and likely UV damage as well. It may also be providing some fire protection for this. This has been seen as we're seeing more and more insulation required, particularly for continuous insulation, making sure that we are protecting against fire in case we do end up with a building fire in the future. So that kind of covers our footing and foundation insulation. So next up, we're going to move up to the thermal envelope. So now we're moving into that rim joist area on up from there. So with thermal insulation and the thermal envelope, this may be done as far as 2 parts for an inspection. So again, check with your municipality as far as how they would like to do this. Sometimes they will do this as a single inspection. Some may do it as 2 inspections as part of their other inspections that they may be doing. First being a framing and structural and air sealing, and then later doing an insulation inspection. Because insulation commonly hides or covers over air sealing details, which make those much more difficult to observe without removing the insulation from the cavities. And if you're missing some air sealing details, it's a whole lot easier to remedy that before the insulation is installed than after the fact. So once you have your framing in place and all your exterior penetrations are made, that is one opportunity that you may have if you choose to do a blower door test, is to do this as early as you can, just to do that verification of that envelope. We go through and verify all kinds of other systems in our buildings, from the fire alarm system to the sprinkler system, many different systems. We verify performance. So doing a blower door or pressure test to do verification of your envelope performance can be very effective. So again, being aware that once you have insulation covering it up, it makes it much harder to determine if you have air leaks, where they're actually coming from. So with this, we're going to be checking a lot of different aspects of this, as noted here. On the left-hand side, we're showing a metal frame building, and they're insulating it from the inside using a sprayed-on product rather than a liner system, which may be some more common methods. And on the right-hand side, we're showing where this air seal is going, where the foundation is meeting that wall cavity, and here again making sure that we're following manufacturer's procedure. In this one example here, they require the wood to be primed before application of this sealing tape, and then they would probably require that it be rolled afterwards. So again, making sure that that is going to adhere well to that substrate. Definitely don't want to try to avoid seeing peel and stick membranes becoming stick and peel membranes. So similar to our foundation, we're going to be first checking the type of insulation that's going to be used. It's not uncommon for this to be different types of insulation in different locations. So the wall may have a different insulation type than the roof, which may also may be different in different locations. So you may have one area of a wall that's a masonry wall that's insulated one method, and another area of the wall that's using insulated metal panels, for example. And so what the inspector is checking for is, did we use the correct type of insulation based on the design? So if the architect had called for the entire exterior to be insulated metal panels, and then you go out and do the inspection and you find stone wool insulation installed, that's not a match, which may or may not be an issue, but considering, is the insulation supposed to be the vapor barrier? Some insulation products out there are a vapor barrier, and so if you install the wrong type of insulation and the design is counting on that insulation to provide that vapor barrier, and you use a different type, the vapor barrier may be ineffective or inadequate, depending on the design. So not necessarily an issue to have different insulation, but being aware of that vapor property of it. Also very similar to the foundation, once we've verified the insulation, checking, do we have the proper R value? Did we match the design? Again, higher is better. Nothing wrong with over or insulating a building beyond, a little bit beyond what it's specified. But checking, do we have the proper depth? We don't see as much blown-in insulation in commercial facilities, but for blown-in insulation, making sure, do we have the appropriate number of depth gauges? Need one at least every 300 square feet, and we need to make sure that they are affixed to the joists or trusses. If they are not, you can actually get slouch in the depth gauges, as depicted here in the photo on the left, where even though it's the actual depth is 3 inches less than the depth shown on the gauge. That could really be an issue if it specifies that you need to blow in an R32, and here on the gauge is saying, okay, that's 12 inches. However, 12 inches is actually up at the 14-inch mark. So again, making sure that we've properly affix those gauges, and so that the 0 point is actually starting at 0 depth. So if you do use a blown-in or sprayed-on product, then you do have to have a certificate signed and posted. This may be posted at the entry to the location, such as an attic as depicted here, or that may be found at the in the location of the mechanical room by an electrical panel or some other suitable location. So that way people know what type of insulation is there, how thick was it, and what was the total R value. This can provide some additional benefits over the time as buildings may be changed or improved, and understanding that what was there. And so if you see that, it was originally applied to be 3.5 inches, and you go up into the attic and you find the insulation level is 5 inches, then you know that some additional insulation has been added over time, which can impact sizing for heating and cooling equipment. Also going to be checking as far as where is the insulation located. Is it located on the floor, or is it part of the roofing assembly? Is it continuous versus cavity insulation? Here on the left, we're just depicting some sprayed in cavity insulation. In commercial buildings, it's not uncommon for insulation to be above the roof deck, completely above the roof deck, either being on a low slope roof or even on some pitched roofs, to see continuous insulation above the roof deck. And so this is probably less of an issue in commercial locations where it might be specified on the floor and they installed it on the roof, or vice versa. But this can have an impact, again, on that HVAC system. If it's trying to serve more condition, more area, and more volume than it was originally intended to. Also going through and checking, did we have proper installation? Again, filling the cavity and without compression. Here we see some various illustrations on the left where we didn't quite have enough, and so we just kind of made it stretch and tried to make it appear filled, even though it missed the mark. Towards the right here, we have compressed insulation. So again, checking for these installation details can dramatically have a role on the envelope performance over time. Also looking for the fenestration. So now that we've gotten through our walls and checking for our thermal insulation, now moving over to fenestration and checking, do we have the appropriate labeling for site-built windows? Those need to also be rated, and that rating needs to be provided to the code official. So this is something that NFRC does have a method to provide that. So here on the left, we see what may be used for a site-built product, where the specific product is rated based on the particular installation, and then that information may be provided to the code official, as opposed to what you may be familiar with on more residential grade windows or factory built windows, where you'll just have that NFRC sticker. So first checking is our U factor. Again, does it match the design? Here, because U factor is about thermal transmittance, whereas R value is resistance to energy. Here again, lower is perfectly fine. Is a window that transmits less energy is a better design. And then also our solar heat gain coefficient, checking, does it match the design? This is one where definitely should match the design, because heating and air conditioning systems may take advantage of solar heat gain and or shading as appropriate. And so if you have a design and the solar heat gain coefficient is supposed to be a 0.3, and the window that gets installed is a 0.15, that could have a negative impact on the building's comfort and heating and cooling systems over time. So just being aware of that and making sure, did we match the specification for that? Visible transmittance is another one. Does it match the design? This is a little less critical, but being aware where this can play a role is when we get into daylight harvesting controls. If you don't have enough visible transmittance and you're not allowing enough natural light into the building, that's going to cause the artificial lighting to work harder. So something else to be definitely checking for fenestration is, did we get the proper seals around the window? This is something that best practice has changed over the years, and so being aware as far as what is best practice today. Here on the left, we're showing that this window is not caulked at the bottom. And then towards the rear of that, we see there is a bead along with caulking. So we have some backer rod with some caulking to provide that air seal. So being aware that for fenestration, we have at least two different needs. We need to control bulk water and we need to control air. And so best practice now has shown that moving those two seals and that two needs apart actually has improved performance of buildings. And so the outer seal being for water and the inner seal being for air. And for water sealing, we want to make sure that we have sealed the two sides and the top of the fenestration. We do not want to seal the bottom for water. What that allows for is, if water does penetrate this seal and gets into this chamber, it has a way to get around the window and back out. And so by moving that air seal to the inside of the fenestration and having the water seal to the outside, this chamber between those two seals is pressure moderated. So it's going to be at a similar pressure to the outside condition. And so even wind and driving rain, this outer seal is going to not see a substantial pressure difference. So it's only trying to keep water out, which it's much easier to do when you have the same pressure on both sides of your seal. Whereas the inner seal providing that air seal, that allows your air barrier to be continuous, and that inner seal avoids UV and most of the weather degradation. So that allows that inner seal to remain in much better condition over the life of that building. So, here's some details showing some site-built windows. Again, here noting that's an interior air seal, and then there's that exterior seal. So trying to, again, keep those two interfaces, the water barrier and the air barrier, separate, and maintaining that pressure moderated cavity. Something else that going to be checking for as part of this is, do we have the proper air leakage controls for windows? Windows are rated as far as air leakiness. And so part of this is checking to make sure were they installed properly. They should be able to, windows that are operable should be able to close, and the locks should be able to engage. The locks are part of that testing process for fenestration, and so that air leakage test is generally with those locks engaged. So understanding that. And on the right here, we show one of the benefits of doing a pressure test on the building is seals that may not have been quite fully seated during an envelope pressure test. Those seals might pop out of place and present themselves as saying, "Hey, I wasn't installed properly. You know, I need to be need to have some attention addressed. So that is, again, making sure that we go through and do that air barrier testing can be very valuable for commercial buildings because they do have a lot of site-built windows, and so making sure that all those gaskets were installed correctly. For our air barrier, checking our thermal envelope and making sure that we've addressed, previously we've focused a lot on dissimilar materials because we do have differential thermal expansion and contraction. But more commonly now, we're, because people have gotten good at identifying and sealing the dissimilar materials, is understanding that we need to make sure that the joints of similar materials are sealed appropriately. And understanding while they may not have the differential of expansion and contraction that dissimilar materials may have, if we don't seal those joints, again, that air barrier can be compromised. So, also checking to see, did we have the proper joint materials? Because we do have expansion and contraction, want to make sure that we're avoiding joints that have movement using sealants that don't allow for that expansion and contraction movement. A good example of this is exterior walls that have been grouted rather than using caulking or other flexible sealing material. That grouting can be penetrated with water and popped loose. So again, wanting to make sure that using elastomeric or other flexible sealing materials are used as far as these joints. So with that, I believe we've got a poll question here. First question is, if sheet insulation installed with full Z channels can be considered continuous insulation, yes or no? Number 2, which of the following components needs to be on the NFRC label? Choose all that apply: U factor, solar heat gain coefficient, visible transmittance, air leakage rate, or comfort rating. And it looks like we have a question that came in here, I believe.
I was muted. I was just asking the question. But for mixed use buildings, a lot of apartments now will have a commercial storefront on the first floor, first 2 floors, and then apartments above that. Those buildings would fall under the commercial provisions for the envelope. Certain components, such as mechanical ventilation rates, might fall under the residential provisions. But by and large, those will have to meet the commercial provisions for the envelope and a number of the mechanical systems. Particularly if those systems are sharing mechanical units. If the apartments have individual mechanical systems, they would fall more towards the residential provisions. Looks like we've got most of our poll answers in, so we'll share those results.
Okay. First question, if full Z channels breaks the continuous insulation, and most people picked up on that yes, that full Z channels do not allow insulation to be considered continuous insulation. Again, you have that continuous bridge, it's not just the fastener. And for question number 2, which of the following need to be on the NFRC label? Most people picked up on it. It is all of them except for the comfort rating. Again, part of that is what is comfortable to one person may not be to someone else. So that's a much more subjective thing. So with that, I'm going to turn it over to Sean to touch on plumbing and mechanicals.
All right, thank you very much, Ryan. The first thing we're going to touch on are commercial plumbing systems. So when you're going through and looking at your site inspection, number of things that you're going to be looking for: types of insulation and level of insulation on the plumbing lines, the corresponding R value of that insulation, whether that insulation is properly protected from weather, UV, mechanical damage, the required controls on the plumbing systems if you've got circulating hot water systems, and heat traps on the hot water storage tanks. So first thing we're going to go over are the types of insulation for HVAC systems, chilled water lines, hot water lines, steam lines. You're probably going to see more of the fiberglass wrap with the all-purpose coverings on them. For domestic water lines, you might still see some of these expanded foam wraps that go around that insulation. What we want to highlight here is that where you've got angles or joints, T's in that insulation, you're going to want to form those joints with miters so that you're not putting additional stress on this insulation, which may compress it and thus reduce its R value, or put tension on it, which would also compress that insulation in the tension spot, reducing its R value, but also put additional stress on it and cause that insulation to wear out faster over time. So that material will start to pull apart. As we go through buildings and do retro commissioning projects, typically where we see insulation damages on the outside of bends, and then in some instances where people use the piping as ladders and try to climb up to higher spaces, and they'll wear down that insulation. But making sure that those wraps are properly installed where you're not compressing that insulation, maintaining that full thickness for that full R value is important for the overall performance of the system. The corresponding R value of that insulation needs to be checked. One thing we want to note is that for most commercial systems, prescriptive code requires a minimum of R3 insulation on piping insulation for hot water. For this particular manufacturer's insulation, notice that that 3/8 inch wall insulation does not quite meet that R3 requirement. So the 1/2 inch wall insulation would have to be installed. You're getting a little additional benefit going beyond that R3, but that is the minimum requirement. So it's important to pay attention to that when you're doing the installation, that you've got that proper thickness and that proper R value. Some of the more common locations that pipe insulation is required: the suction and liquid lines on refrigeration equipment. These are common issues that we see for VRF systems, mini split systems. These refrigerant lines, typically the cold line is well insulated, well protected, but the hot liquid line is exposed. Where this is inside the building, this will dump a little bit of heat back into the building. On the outside of the building, it leaves that pipe exposed to corrosion, weather effects. So again, that line does need to be insulated, both the hot liquid line and the cold suction line. It's important for the overall performance and efficiency of the HVAC system. Another place where we typically see insulation is near hot water heaters. You've got point of use heaters or large storage tanks. Again, typically we see insulations trimmed away from the tank a little bit. Some people are concerned about that insulation kind of melting due to heat, especially on gas units near exhaust vents. But if properly installed with the proper insulation, that should not be a concern. Also, if the gas systems are properly vented. Now that more and more systems are moving towards high efficiency enclosed combustion, that's also less of an issue than when we had open combustion flues on water heaters that could backdraft and cause that insulation to melt. But important to fully insulate all the way down the piping, all the way up to the tanks where the tank is insulated. So you've got that continuous insulation throughout that system. As far as protecting the insulation on these plumbing systems, the insulation does need to have protection from physical damage, UV damage, weather effects. There's two types of jackets we're showing here. The white all-purpose PVC jackets, a little more common for, again, chilled water lines, larger hot water lines, insulation that's exterior to the building. For smaller refrigeration systems, copper lined systems that have those kind of peel and stick around insulation wraps. They do make wraps for protecting that insulation as well. It provides a little UV protection. One of the things that the Energy Code does note is that these need to be removable. So you could not use a taped system, as that would not be removable. You need to be able to facilitate maintenance and repair of these lines. So that jacket does need to be easily removable so you can access the insulation underneath, remove it, get to the pipe if you ever need to seal any leakage or do repairs to the system. Moving on to controls. Uh, Here we're looking at controls for hot water circulation systems. If you do have a hot water circulation system, the Energy Code does require controls that are based on demand in the building. So we're looking at here is that timer systems are not allowed for hot water circulation loops. There does have to be some demand component to that hot water flow sensor. Um, Usually it is a flow meter on the cold water inlet to the hot water storage tank. That way, as the tank has hot water drawn out on demand, cold water is drawn into the tank. That flow sensor picks that up and records that as demand for hot water. That will activate your circulation loop pump. Those circulation loops will then pump until one of two conditions. If you've got a continuous circulation loop, then that pump will operate until the loop is back up to its set point temperature. If you've got a demand circulation system, then that pump will turn off after a few minutes after occupancy or usage of hot water has been, a signal has been deactivated. So usually that occupancy sensor is going to be some kind of flow switch, an occupancy sensor in the restroom, a push button toggle that's going to kick on that demand circulation system. That distinguishes it from a circulation system, which is triggered by that demand for hot water at a central storage tank. The next thing to be aware of is heat traps. When you're looking at plumbing systems, you don't want hot water siphoning out of your hot water storage tank into the distribution system to the cold line or the hot water line, as that will result in significant energy losses. So these storage tanks on both commercial and residential systems are required to have heat traps in them to prevent that kind of hot water buoyancy, causing siphoning of hot water out of that storage tank and energy loss. We did have one more question come in before I move on to mechanical systems about for refrigerant lines outside the building, is a jacket required? Yes, you do need to have on refrigerant lines some kind of UV protection for that foam insulation. That's probably the most common degradation we see, is that UV causes that foam to dry rot over time and then it crumbles away. Usually what we've seen in the past is a paint on UV protectant for that foam insulation instead of a jacket. If a paint on UV protectant is used, it needs to be reapplied every couple of years at a minimum. And that doesn't usually get done. It's not highlighted to the building owner. So the code has specified that there does need to be a jacket system that is removable on that insulation to protect it. And as we noted, there are systems out there specifically designed for those refrigerant lines. Moving on to the mechanical system site inspections. There's a lot to check here, especially in commercial buildings, as we get into more and more complex controls to achieve higher and higher energy efficiency of our systems. We need to verify the HVAC equipment type matches the plan drawings, the size, capacity of those systems matches, the required controls are in place as far as economizers, temperature sensors, demand control ventilation, proper system insulation is in place on ductwork and mechanical piping. Corresponding R value of that insulation is correct. The system and damper air leakage controls are properly in place and documented for both dampers and for duct installation. The minimum fan efficiency is correct. Energy recovery devices are in place where they are required. and the economizer is in place where required, properly set up for the type of economizer that's installed and the design outdoor conditions. So there's a lot to go over here. Commissioning is the process that goes through and verifies that all these controls are set up properly, both for mechanical systems and later on when we touch on lighting, it also checks on the lighting system controls. And it's a daunting task to go through and check all the various points in these building systems. Initial commissioning report may be reviewed during rough-in inspections for HVAC systems. They check on some progress and check on functional testing as well for systems that are installed and brought online. And a lot of facilities that I've worked at that were under construction, this was kind of an as completed process where they commission those systems as they're brought online. Although I've also seen it done for smaller buildings where it's kind of a lump thing. Once everything is up and running, then the commissioning is done as a lump project. So it just depends on the complexity and the size of the building, which path is going to be most beneficial as far as saving you time overall and completing the project. Per the Energy Code, Section C403 and C405 contain the control requirements for those systems. The commissioning plan in place needs to verify that all those required controls are installed properly, working properly, and have been properly commissioned and tested. There is a lot of automation, again, as noted, more and more relying on automation to achieve higher efficiency in our buildings. So we've got thermostat settings, unoccupied setbacks, demand control ventilation, economizers, freeze protection systems, all need to be checked and documented. So having an effective plan in place early is very important. Usually what we see is in control drawings. As those are developed, they're also used to develop commissioning checklists. So as you have sensors for controlling an HVAC system drawn out, those sensors get documented that they need to be tested and verified. The control sequence gets documented, how the sequence is supposed to work. Those all get drafted into a commissioning plan. The commissioning plan documents all those different sections of the control sequence for that equipment. And then that is what the commissioning agent will then go back through and use as the commissioning checklist. One thing to be aware of is if your building is using heat pump equipment, this does add a little bit of additional complexity to your verification as you add that reversing valve control to the refrigeration system. So it's one more component that needs to be checked for proper operation. Another thing is that those systems will have to have some kind of electric or gas backup system. The controls for that gas backup or electric backup system need to be verified that they're not going to be kicking on when the compressor can handle the loads in the building. They're only going to kick on when those loads exceed what the compressor can handle for heating. And that they're also not going to be having issues with that reversing valve or a situation where you might have simultaneous heating and cooling with those backup systems when the system is in cooling mode. So just making sure that the sequence of operations is correct on those heat pump units, that backup emergency heating is only going to be operating when it's needed, and that reversing valve is working properly. Probably the first thing that's going to be checked on your mechanical systems is the equipment size. Does it match your design? Does it match what you had in your initial comm check for compliance verification? What we've done here is pulled out a section of the report that's showing in the comm check what the initial design is for two different air handling systems. So as an inspector is coming back through the building and looking at the mechanical systems, you're going to be verifying that they're as close as possible to these design values that are listed in CommCheck. There may be some limitation on these design values as far as the marketed size for equipment systems. It may be the next closest available size to these, but they're going to be verifying that as close as possible with the available equipment that these values are met. And the main reason for that, again, as our buildings are becoming tighter and more energy efficient, load calculations are much more important for ensuring that those systems um, aren't going to have issues with short cycling, humidity control. Um, they're going to operate at peak efficiency. Um, so that's the main reason for checking on the capacity of those systems. The next thing it's going to be looking at is all the controls on those individual HVAC systems. Are the ventilation controls properly functioning? Are temperature controls in the space properly functioning? So with thermostats, need to be verifying that they have the proper deadband setting to prevent simultaneous heating and cooling with reheat systems. Um, need about a couple degrees between the heating and cooling minimum set points for airflow and for activating that reheat valve. Um, for setback conditions, you need to verify that those temperature settings for setbacks are in place and that there is some kind of setback schedule for the building when it's in an unoccupied condition. Um, for ventilation controls, you're looking at the economizer operation. Is that going to be bringing in free cooling when it's available, ensuring that it's not going to be bringing in outdoor air that's too warm and actually increasing cooling loads, or air that's too cold and increasing heating loads. Going to be verifying that minimum ventilation requirements are met as far as ASHRAE's ventilation standards. Uh, there's a lot to check here. DCV controls, making sure that they are working properly, that DCV isn't going to override your economizer. The economizer should be overriding the DCV system so that when you've got free cooling, you don't have the DCV system saying, well, I don't need any more outdoor air and shutting off that free cooling potential. You want the economizer to override the demand control ventilation instead. So a lot to be aware of. Other things that are going to be checked are damper controls and zones for the HVAC system. Each zone needs to be controlled independently. So there should be air shut off to individual zones. So you're going to be looking at the tightness of those air dampers, making sure that they can actually seal off airflow, that they can also control airflow within the zones as needed for temperature control purposes and at minimum ventilation purposes. Once you've gone through and checked all the controls are properly in place, properly working, that there's a commissioning plan in place to verify those, then we're going to be looking at the HVAC system's installation for ductwork. Where it's outside the thermal envelope, you're going to be checking for proper insulation is installed, and that insulation again has proper protection from UV and mechanical weather damage, particularly for rooftop systems that might have any kind of exposed ductwork on the rooftop. For any interior unconditioned spaces, such as chaseways, outdoor vented mechanical spaces, tunnel systems that might be semi-conditioned or unconditioned. Again, checking that insulation has the proper insulation values on it. And for commercial duct systems, duct sealing is required. However, duct testing is not required, at least not yet. Except for high pressure systems where the design pressure in that ductwork is over 3 inches of water, in which case there is a Sheet Metal Manufacturers Association testing standard for that high pressure ductwork. But for most commercial buildings, the duct systems are designed at the 1 to 2 inch range. It's exceedingly rare to see a commercial building with a 3-inch duct pressure design, unless you've got a high velocity system. And so again, as the code official is going through the building, he's going to be looking for proper duct sealing, making sure that joints are properly masticed or taped, that those mastics or tapes are UL 181 rated, so that they're going to provide that lasting seal in the duct system. For duct insulation values, does that meet the right design? For the prescriptive path, you're going to be looking at R6 or R8 insulation in an attic space, R4.2 or R6 in other locations, such as crawl spaces or unconditioned areas in a building. That lower value is for ducts less than 3 inches in diameter, so the R6 and the R4.2. For ductwork that's above conditioned ceilings, that conditioned ceiling space above a drop tile ceiling or T-bar framing for a ceiling is considered a conditioned area, so duct insulation is not required, although it is commonly installed for sound dampening, and we do recommend some amount of insulation for condensation control on that ductwork. Recognizing that with tighter building envelopes, we should not have outdoor air leakage into the above ceiling plenums in these spaces. But it's usually some instance of outdoor air leakage gets into these above ceilings, especially as they are used commonly as open return plenums for HVAC systems. They are depressurized. They are very, very likely to draw in outside air from envelope leaks. And as you draw in that outside air, you also draw in that uncontrolled humidity. We have seen instances where uninsulated ductwork has developed condensation and created what look like roof leaks on the drop tile ceiling. So again, usually if there is insulation on that ductwork above a T-bar ceiling or drop tile ceiling, it's there for sound dampening control. We do recommend it for a little bit of condensation control, but it's not required by the code. As far as duct sealing, again, making sure that you're using a UL rated tape or mastic on all the joints in that duct system, making sure it's properly sealed to avoid leakage. Make sure that the air you're conditioning gets to the spaces that need it. And the other thing that the code official is going to be looking for to verify is that shut-off dampers for ventilation controls are properly rated with a proper air leakage rate. Usually it's a label on the damper that's easy to check. But you're going to make sure that those dampers actually have full range of motion, that they're going to be able to fully close and seal with the proper pressure so that they actually meet those air leakage ratings that are on those damper systems. HVAC fan efficiency. This is something that can be a little bit confusing. This is not the efficiency on the motor nameplate. This is an efficiency rating for the fan wheel itself, as far as how much of the mechanical energy supplied to the fan gets converted into motive force for the airflow. Where this is shown typically is not what's circled on this particular report. See if I can find it on the screen here. I don't actually see it on that screen. But there is a fan rating for fan efficiency factor that, again, it's a factor that's relating to the fan wheel's efficiency of converting motive mechanical force to motive motion of airflow. But another thing that does need to be checked is that the fan system's rated horsepower complies with the energy code's requirements. There is a calculation based on the CFM supply rate for a mechanical system on what the maximum combined horsepower for the supply, return, and exhaust fans for that system should be. And that is contained in a table that's easy to look up that calculation for those fan systems. One thing that's very important to note here is that as you're checking that these fan motor requirements are met, duct leakage is of a concern here because as you're limiting the horsepower of these fans, that's based on the assumption that the ductwork is tight enough that you're not going to be increasing demands on this system from air leakage beyond what the fan motors can supply to the airstream. So if you don't have tight ductwork and you've got supply leaks into a plenum, especially if you've got open return plenums where you short circuit that supply air directly back to the air handler, that can actually increase the horsepower requirements for those fans by 3 to 5 horsepower if that ductwork isn't properly sealed. And so as the energy codes have become stricter on the requirements for the horsepower of these fan motors, the duct sealing component of the system is also becoming much more important to ensure that these systems work properly. Next thing that we're going to be looking at is an energy wheel. It's probably the most common system that we see for energy recovery systems. Um, Also, for energy recovery systems, hot gas reheat qualifies as an energy recovery system. However, hot gas bypass does not. Um, what we've shown on screen here is an example of what a hot gas reheat system looks like. Takes that compressed air from a refrigeration coil or the compressed refrigeration fluid, passes it through a reheat coil that takes some of that heat, adds it back to the cooled indoor air as a reheat mechanism before it goes out to the condenser coil. So it's reducing the load on the condenser coil and reducing the load on the reheat system of the building. Um, that's an important distinction between a hot gas reheat system and a hot gas bypass system. The bypass system just bypasses that condenser coil. But where these mechanical systems are required, you want to make sure that the energy wheels or any kind of energy recovery system has proper controls on it, that it's not going to, again, override the economizing of the HVAC system when that's available. There's nothing worse than taking your 55-degree outside air, exchanging with an energy recovery wheel and adding 20 degrees to it or so, and then having to cool that air back down. So as part of your mechanical system checks, they're going to be looking to make sure that energy recovery system isn't overriding your economizing system. You want it to go the other way around. Something else to be aware of is that even though there are certain instances where energy recovery wheels are not allowed, particularly when you've got exhaust fumes that may be hazardous if they were re-entrained into the outdoor fresh air stream. There are other energy recovery options that are available. They're not required by code, but they can save the client a lot of money, particularly now in this age of the COVID pandemic when we're looking to increase outdoor air ventilation rates for buildings as a means to control pathogen spread. Um, there are other systems such as flat plate heat exchangers and runaround loops for cooling energy. They're typically used in lab systems where you cannot exchange air directly from an exhaust airstream with an energy wheel or an energy heat exchanger, because those systems would potentially allow some mixing of the exhaust and outdoor airstreams. So particularly clients that are looking for more outdoor air in a cost-effective way, there are other ways to add that air, particularly kitchen systems that may have a lot of grease, runaround loops, or other heat exchange systems that exchange sensible heat may be more economical now. For your HVAC economizer, again, we're checking for proper settings, proper operation, and full range of damper motion. We want to make sure that those dampers can close off properly so that you don't have leak by on that system when you're calling for full outside air. You don't want some of your return air still mixing in, reducing the effectiveness of that economizer system. When you're calling for minimal outside air, you want to make sure that those dampers are then not fully sealed so that you're getting that 20-30% minimum, whatever that ASHRAE minimum outdoor airflow rate is. So those are things that are going to be checked as part of that commissioning process and as part of the code compliance process. Something else that will be checked is that the high limit cutoffs are properly in place on these systems. Again, you don't want the economizer operating in a condition where it's actually adding to the energy load of the building. And that's what that high limit cutoff is looking for. And low temperature cutoffs as well. You don't want the system operating when it could freeze coils within the building. You want usually the systems to be dropping to a minimum outside air condition when there's that potential freeze risk. And we have another poll here on the plumbing and mechanical section before we move on. So we'll launch that poll. The first question, is time-based domestic hot water circulation acceptable as a control method? And the second question, which of the following are part of the mechanical inspection? Duct insulation R value, energy recovery, equipment physical size, damper air leakage, duct sealing, or heat traps? That is a multiple choice question, so select all that apply. I don't see that any questions have come in. So we'll let this poll run and then we'll jump into our electrical systems. Okay, looks like we've got most of our responses in, so we'll go ahead and share those results. For the first question, looks like most people got that correct. Time-based controls are not allowed on hot water circulation systems. It has to be a demand-based control, either a flow sensor on the cold water inlet or for a demand system, some kind of demand sensor within the space for hot water. And then for the mechanical inspection, all of these are components of that mechanical inspection. It looks like some of these were dropped off. Equipment's physical size is not a requirement. The capacity of the system is a requirement for that inspection. So that is the one exception on this list. The physical size of equipment is not part of that energy code inspection. So it looks like people picked up on that as well. All right. So now we'll move on to the electrical system with Ryan.
All right. Moving on to electrical. So we've got a few things to check for the electrical. This is a fairly short list, but it gets very involved, particularly for verifying that all the different system controls are in place. For those of you who are familiar with the code, most every space in a commercial building requires some form of lighting system controls, either occupant sensing controls or time switch controls. Some spaces may have both. That's perfectly fine. But the code requires one or the other in nearly every space in a commercial building. And so checking to make sure that all of these are in place. So this may be something as you're walking through a building and being aware as far as some of the various control strategies that are out there. And so this is something that it should be as part of the commissioning documents, and something to be aware of is when we say commissioning, and this applies both to lighting controls and to the mechanical systems, this is more than just functional performance testing. It's more than just do the dampers open and close. It is checking sequences of operations as far as, when X, Y, and Z happens, does the system respond appropriately? And so similar here for lighting control systems, walking through, and not that a code official is likely to check every single one of these. That is where your commissioning professional comes into play, is they need to go through and commission every single room, all the different controls and the like. And so the code official may likely spot check some of these from the commissioning report and check, is the do we have the appropriate manual on or off? Do we have dimming as appropriate? Do we have the daylight harvesting in place? Is this supposed to be controlled by a time clock? And if so, is the time clock present and programmed for that? So going through, as you can imagine, between your occupant sensing controls, your time switch controls, and potentially daylight harvesting controls, if for projects that have not taken advantage of the exception to eliminate the need for some of the daylight harvesting controls. That is a lot of commissioning to go through room by room by room. So that's where this is for the electric side. It's again fairly straightforward, but it can be very time consuming. So once we've gone through and checked and being aware, are all the system components in place? So my occupant sensors, if I walk into a space and the lights come on automatically, did they come on only to 50%? If they came on full on, am I in one of the few areas that the code allows for full on for auto on switching. Some of those are like bathrooms, corridors, and other similar spaces like those. Stairwells is another one we get into. But for most locations, if the lights automatically come on, they can only come on to 50%, and then the user has to interact with the control in order to bring on the other 50% of the lights. Or if it's a vacancy type sensor or type of occupant sensing device where you have to interact in order to bring the lights on at all, that can go to 100%. So being aware is part of that walkthrough is, did the lights come on automatically, or did I have to do something? One of the other checks that would be is, are they located appropriately? If I have an occupant sensor in front of me and I'm in an office and you see I've got a door or potential hallway behind me, with that doorway being open, if I have people traveling by, is it likely to trip that sensor? So making sure that the sensors are located such that they're not going to falsely trip just from someone passing outside of the room. And similarly, the daylight sensors here on this second graphic here for daylight harvesting controls, are they located in an appropriate spot where they can quote, see the amount of available light in the space so they can control properly. They're not tucked behind a beam in a corner such that when the light comes in, it won't be able to observe it and control appropriately. Time switches, generally most buildings are going to require 2 of them, depending on which control methodology they select for their exterior lighting controls. But there's likely to be at least 2 for exterior lighting, and there may be an additional one for interior lighting controls. So do you have all the appropriate components in place, the appropriate number, and then for exterior lighting, not only do we need our time switch controls, but we also have to have daylight shut off. So we don't want to run our LEDs outside in the middle of the day when it's during the heat of the day. That's very hard on LED fixtures. So that's part of the reason why the code now requires both time-based and daylight shut off, just to make sure that we don't run them during the middle of the day. Next up would be the electrical system. Do we have the appropriate electrical meterings? So this is for R2 occupancies. So if you have more than 2 dwelling units, commonly these are handled for most buildings by utility meter stacks, such as depicted here on the right-hand side of the slide. For larger buildings, they may choose to have more centralized sub-metering rather than having it all billed out to the utility to handle all of that. So that's perfectly acceptable too. But just being aware, do we have the appropriate metering in place as required? So yeah, lighting, the lighting and electrical inspection is going to be fairly brief. The one other thing that I should mention in here for the electrical is pertaining to elevators, is checking to make sure that the elevator shut off occurs, which I believe is within 15 or 30 minutes of there being no one in the elevator, that the lights and fan shut off when the doors are closed. Obviously, if there's no one in there, the elevator cab will not get scared of the dark with no one there. So with our final inspections, so this is covering anything and everything that may not have been captured earlier. So this may be a second capture for the commissioning of the HVAC systems. So generally during mechanical inspections, there may be the preliminary report of commissioning, as far as just that may be more of the functional performance testing phase of it, is just saying, is everything working? And then during final commissioning, documenting that the final building commissioning has been completed prior to this final inspection. So that would also include the assessment here that we show on the right here, checking through, is everything functioning, and also commenting any deficiencies that were identified as part of that. So these would be punch list items that would end up being needed to be remedied before or shortly after the building owners taking possession of the building from the contractors. So again, checking to see, do we have that deficiency report? If the commissioning hasn't proceeded such that they're able to generate the deficiency report, then this building is not ready for a final inspection yet. So as we're going through from there, checking any remaining equipment controls that we haven't checked previously. So anything that was, again, identified on any earlier inspections as far as deficiencies, have we gone through and remedied that, or were we missing any controls during that? So this could be exhaust fan controls, maybe CO2 and ventilation controls. Again, making sure that we have all of those in place. And then one of the final things is all the documentation. Again, here, this is talking about the building commissioning. There's also the requirement for operating and maintenance documentation that needs to be turned over to the building owner within 90 days of the certificate of occupancy. How we have seen several jurisdictions handling this is one of the requirements for the final inspection is a letter from the building owner stating that they understand they should be expecting this documentation. While the code official doesn't really have a good mechanism for enforcement, at least the building owner is, they've made the building owner aware that they should be expecting this documentation, such that the building owner, in the event that the documentation is not received, knows to follow up with their contractor to get it. So with that, sure if we'll have a few other questions come in. I did want to touch on that first question that came in regarding mixed residential and commercial buildings. I did want to make sure that we have the full clarity on that. The code does call out that buildings that includes both residential building and commercial building portions, each portion shall be separately considered to meet the applicable provisions, either the commercial or residential. So in, I believe, the example earlier that Sean mentioned, where you might have a store on the first floor with one or two floors of apartments or residences upstairs, that first floor would have to meet the commercial provisions, and the residential second and third stories above would have to meet the residential provisions. So just wanted to make sure that we were fully clear on that.
Thank you for correcting me on that. I believed it was otherwise. We do have one final poll here. We'll launch that now. For lighting controls requiring inspection for the energy code, which of the following is included? Occupancy sensors, daylighting responsive controls, light switches, time switches, decorative lighting shutoff. And then when does the initial commissioning need to be completed? Before the mechanical system inspection, before the electrical system inspection, or before the final inspection? I'll leave that up on screen for a few moments. Again, if you have any further questions for us today, please enter them in the question and answer window. Otherwise, if you want to reach out to us for a more detailed question, please use that energycode@illinois.edu email address. Let us know if it's a commercial or a residential project, and we will be glad to get back with you with an answer.
Also, the location of the project would be helpful too, so we understand if we're in a climate zone 4 or climate zone 5.
Very true. Okay, looks like we've got most of our poll responses in, so we'll go ahead and share those results.
And as far as lighting controls requiring inspection, uh, include the following: occupant sensors, yes; daylight responsive controls, yes; light switches, no; time switches, yes; and decorative lighting shutoff. So I realize light switches is a little bit of a weird one because most occupant sensors are light switches too. So, but yes, everything but light switches on that list. And then as far as when does the initial commissioning need to be completed, most everyone got that before the final inspection, because that initial commissioning, that's when you're going to be generating all your punch list items and things that need to be remedied.
All right. Well, seeing did get a comment in the chat there. You need manual switches with the occupancy sensors, but they
Yep.
do not need to be inspected by the inspector.
Uh, yeah, that is something that occupant sensors do require a way to turn the lights off. Frequently, those are built into the switch itself, where there's a button on the occupant sensor that's on, at least for wall-mounted ones. So yes, there does need to be, with occupant sensors, you do need a way to turn the lights off for most areas.
Seeing no further questions coming into the Q&A or the chat, we would like to thank everyone for joining us today. We hope you have a wonderful afternoon. Thank you.